So, okay, let's just take on from where we left 15-20 odd minutes ago. So, hopefully you could understand that what this block picture means, so on and so forth. And now, the whole point is that given a graph, there is, if some data are sitting on the nodes and edges, after one iteration of this update rules or passing through a GNN block, the data gets updated. Okay. So, there is a nice intuitive visual way to check this. Let us say you were given a graph like this on initially on where there was one node on which there were some data and the other nodes were empty, which means there were 0 data on top of it, and 0 data I mean 0 value of the data. So, it can be, you can think the initial data on this particular red node was 10 and all the other nodes were 0, and you make this message passing operation happens, which is like one iteration, it passes through a GNN and whatever data was there, the nearest neighbor nodes receive the information, the updated information, and propagates. So, this is called message passing network for a reason that there tends to be this pattern that data which is sitting on top of a node sort of spreads to the neighborhood, and on the next iteration it will further spread on other neighborhoods, so on and so forth, and this is how this will propagate. Okay. So, that is cool. In general, the message passing neural network allows us that we do not need to make a neural network heavy, but if we make this message passing iteration like go on for few times, we can really establish some like information exchange between some nodes which is on one far end of a graph, and it's there are some information on some other far end of a graph, and these two pieces of information will eventually start talking to each other via this message passing operation. So, that is the intuitive way of doing graph neural network. Instead of if you were doing a fully connected layer, like if when you do neural network image search, you see this sort of spider nest kind of picture that every node is connecting to each other. That makes it computationally heavy, many more number of parameters. That is not required in the case of graph neural network, and that is one of the advantages. Okay. Now, this has become very much standard in our community, and here you can see an example just for tagging tops. How many different number of top taggers are there with their like number of parameters, and it is a comparison of what is the like background rejection for a particular fixed efficiency. So, you can see there are like regular graph networks, then there are convolutional neural networks, so on and so forth. And nowadays like it is becoming common in our network that the permutation invariance or covariance which we were talking about, you extend it for general Lie groups operation, that there is an input data, you make it some continuous transformation, and can you make a neural network layer where the output is covariant under the action of a Lie group. So, this is now very common, and that is done for like rotations and in general boost, which are called Lorentz graph networks, so on and so forth. And all of them are tried and tested in context of colliders for heavy particle tagging. So, I just want to bring another analogy, that whatever we are talking about graphs, that can be redone for other branches of physics. This is for say cosmology. This is a data from camel simulation, where it is a hydrodynamic simulation of like galaxy clusters, where they inject dark matter halos and things like that and try to see how itself the galaxy structure evolves. But given that's also a point cloud structure, whatever we have learned can be equally applied to this large scale cosmological data structure, and people try to do it every often now and then. Okay, so if you gain some technical expertise and you want to try out your hand in some other domain of physics, that's also possible. Great. Now, let's be a bit more specific that in calorimetry where we do, I mean this is where I started my journey in machine learning, where I tried to do, like there are overlapping neutral pions and charged pions, like shower developing, and I tried to separate them using graph neural network methods. And I also tried to come up with some idea that there is a method called super resolution, which is pretty useful for boosted objects, which we discuss for jet substructures. So the whole idea is that think of there is a calorimeter like detector block, and a boosted particle on flight decays to two collimated objects, which both of them lands up in the same region on the detector, where the spatial granularity doesn't allow you to resolve these two particles. In such a cases, how do you figure out in real life that there were two particles and not one? So that's where we took help of something called super resolution method, that and we established that look, there can be like hadronic showers and pileups and junks, but we can segregate out a pair of photon coming from neutral pions decay, and if there are like two pieces of photons coming from a neutral pion is hiding under this sort of image, we came out with a graph neural network method to segregate that. And here you can see we can make a mass reconstruction as well. So the whole idea is that like for boosted objects, when your detector granularity doesn't allow you to really capture the spatial and angular variation of the ultra boosted object decay particles, then you can apply machine learning methods to do that, and that's called super resolution method. So yeah, the same methods which are now sort of pretty industry standard inside the experimental collaboration for pion identification, hadron identification, so on and so forth. So I just wanted to show you that like what I am talking about is not something very superficial and can't be used. That's not the case at all. Rather, this has become very much standard way of identifying like our reconstruct our individual hadrons and objects and try to tag them. So here are the rock curves which is showing that when we apply some GNN how it performs, and when we apply a transformer which is a like a particular version of GNN how it performs, okay, for reconstruction of hadrons. So these are the like sort of improved directions. If you look into, yeah.
The dotted lines are basically without any neural networks, right? The track resolution.
No, so the dotted network.
So if I just take the lower right plot, track resolution is the one that where two particle goes inside one of the pixel.
No, so this is like for this particular task of identifying pions. So this plot tells you that when you are just using a tracker to identify a charged particle, when the particle momentum increases, the tracker resolution becomes very poor, and hence you can't use just the tracker information to reconstruct the particle. The non-ML method fails. That's this dashed black line. Okay. Now you bring in on top of that information some machine learning method. So there are something called deep neural network, which is like a fully connected network sort of style. So this is this line which is also growing, but it just doesn't diverge. So it says it's doing better than the pure tracker information and using some calorimeter information. And all this rest of the colored lines are comparison of performance between different neural networks where the data is a little bit different representation, which says I have a GNN with no edge is just the deep set, and then I had a transformer network which is recovering this. The takeaway physics message is that there are high PT particle for which charged particle, and if you go through the canonical method of reconstructing them from tracker, then it won't work at all because the track resolution just degrades at high energy.
Yeah, okay.
However, these neural networks can capture information from calorimeters, can correlate them, and get back the response on the right track so that you can do a reliable charge particle identification for high PT particles.
So, okay, this I understood, but this difference that you see at high energies with NN net procedures, why should I rely on these things if I don't know, naively when I think if...
No, so that's where it comes like, these are all done on simulations. What you're trying to do, I have the information of tracker and the information of calorimeters, and I'm asking that, look, my input information to the system is what I can measure, is only the tracker and calorimeter. And can it faithfully reconstruct the momentum of the particle which was at truth level? Since at the simulation level I already know that information, I try to see what my neural network spits out versus what I already had as a truth information. And the fact that this ratio is sort of getting flattened out, it means it's reproducing the numbers which it should have been. So this is like the test data on which we validate the performance of our neural network. Yeah, so that's the point. Yeah. So here it's like simulation, so with all proper detector simulation going on. Yeah.
So that is very important, how
Yeah.
good your simulation data is too.
Yeah, of course. These simulations are cross-checked with the actual data, and these are like GANT which are improved through data-driven way, so on and so forth.
Because your actual data will not give any information because you cannot detect them very well.
No,
as you said, high PT events are not very well.
Actual data we don't have the truth information. Right? It's just as long as we can validate these methods work in a simulation where we know the simulations are very close to data, then once we train a neural network, we can go back to data and then reconstruct stuffs.
So in this plot, the black dotted line is just the tracker.
Right.
So without machine learning also, you already have calorimeter deposits, right? Because
Right.
pion will go to photon, so you have depositions there.
Right.
So including tracker and calorimeter, does it also show such divergence behavior?
Without the ML?
Without ML?
Yes, it will, because tracker itself is diverging, and if you are just building an empirical algorithm, you don't know when to throw away the tracker information.
But
And
why is it diverging? Sorry, I missed.
so tracker resolution, like when a slow particle bends in the magnetic field, if you see how a tracker works, is the motion of a charged particle in the magnetic field. And I have a helix like this. Okay. Now it very much depends on how well you can construct the two ends of like 2 points on a bend, connect this with a straight line, and how reliably you can do it. This is called like Sagittary construction, some blah blah blah. However, if the particle is moving pretty fast, then the amount of bend will be pretty small, and it will be almost like a straight line. So unless there is a sufficient curvature on the tracks, this Kalman filtering based track reconstruction fails.
Okay, but before ML also LHC does have data for pion, so how did they overcome those problems?
No, so in fact yesterday you remember Toshik asked a question when I showed jet energy response at high PT, the resolution was again worsening because
it was going up.
And that was the case, that it was going up and we didn't had a remedy. Now we have remedy to bring it down.
Okay, thank you.
Yeah. So, in our field, CMS also does similar stuff for electron calibration. So, that's like a Z to E mass reconstruction in eCal, and you can see the resolution, it improves quite a lot. Okay. So, this DRN is something, a graph neural network, and depending on the PT, it's like a 10 to 15% improvement in the resolution. So, these methods which I am trying to tell you are very much deep inside our methods, so on and so forth. So, I just want to show you this picture again, taking a comparison with the cosmology, that I showed you something regarding super resolution which we did for detectors, and the same methods are done for like dark matter halo simulation, where you have a low resolution input and they try to build a higher resolution input of cosmological fluids and so on and so forth, where exactly the same principles of machine learning propagates. It's just a different physics problem. But when you think in terms of the machine learning algorithms, etc., exactly the same principle works from input to output, and that works. So, it's like once you master the techniques of these methods, it's quite handy. You can sort of apply on both the fields. Okay. One of the core crucial places where we are trying to improve machine learning methods is something called tracking. Why? What is the problem of tracking? Like bunch of charged particle gets produced. There are our layers like silicon layers. The charged particle on the fly just leaves these dots as a remnant, and reconstruction of track is the problem of connecting this dot. So, if you think of these dots as bunch of graphs where you connect every dots with every other dots in the vicinity, then track reconstruction becomes a problem of age classification. Only one of the dots will be a candidate for a single charged particle which is flying away. So, that's being tried on, and now these methods are tried on different hardwares, not only on GPUs, on FPGA for fast reconstruction, that how you can implement this neural network methods on latest set of hardwares to do this fast machine learning. So, which was like an exponentially like diverging combinatorial optimization problem, we are trying to solve it using graph neural networks. So, that's pretty cool stuff. And here is some details of how do we try, like we exactly implement this age block and node blocks which I was talking about. So, this construction is not superficial construction. These have now direct applications in our field of experimental particle physics, and when we talk about high lumi LHC or future collider, all the tracking methods will be based on this stuff. So, this is quite, yeah.
Implementation of ML in the hardwares. So, do you need to train it first and then implement in the hardware, or is just train in the hardware itself?
No, you can train on a GPU and implement on hardware like FPGA as well. There are methods. Good. Now, like just to show you some performance kind of stuff. So, here you can see that in the Atlas with some machine learning, our like track reconstruction efficiency is like in one case it's 94%, in other case it's almost like close to 1. So, this is the core takeaway information, that the efficiency is not dropping when you are going to higher PT using this method, whereas the whole point of those track reconstruction was when you go to high PT, your efficiency drops, resolution becomes poor. So, this is a live demonstration from Atlas simulation that we can address those sort of problems using machine learning methods, and these are fundamental problems like individual charge particle reconstruction. If that goes nuts, then we are in deep trouble, and we are sort of recovering those sort of problems. Okay. I mean, just not, let's go through again once more. CMS applies something a bit different method, but they also have addressed the same problem. Now, one of the problems which is very close to my heart is the method called particle flow reconstruction. What does it say? It says that what I measured in the detector are these energy deposits in the tracks, and for the quantity where I can solve the physics observables are when I am talking about the particles. So how can I construct a neural network function f of theta in which I pass the information of tracks and calorimeters, and it spits out what are the probable set of particles which has led to this energy distribution. This is the machine learning task I am after, and this is called particle flow reconstruction. This is one of my favorite problems. Okay. So now we have sort of set up a very well defined way to construct this problem. So here you can see an event display that it's sort of a complex event where there are like thousands of particles giving energy deposits every here and there, and you have the tracks, but then you feed it to a neural network and it knows how to tell you the set of particles which are going to do the job. And here you can see some performance plot that there is a canonical method called PF, which is event reconstruction method called particle flow, and then there is a machine learning based version of the same method called MLPF. And when for the same set of calorimeter hits, etc., when you see the output called PF and the corresponding machine learning version, it has quite a good performance in the reconstruction of the events, and hopefully we can make it faster in the future, and we can do it for each type of particle individually, like charged hadrons, neutral hadrons, photons, leptons. So this is remarkable. Like 10 years ago we couldn't have thought about this, and this is kind of game changer what's happening in our field. Now, like if you think of this problem as a statistical learning problem, it's sort of a bit more interesting. What happens are these particles, which I call truth particles, they enter inside our detector. They tend to deposit energies like this. Detector hits tracks everywhere here and there. And what we want to club this information and want to give an output which should be like reconstructed particles. Okay. So this whole causal structure, these arrows, sort of motivates us to go one stage higher. Now we are pretty sure that there cannot be the case that one particle only gives one hit, because you saw many event displays. When an energetic particle enters in our detector, they tend to spread out energy, many different energies. So there should be multiple of these pieces which should be associated with the truth particle. Similarly, when we talk about a reconstructed particle, there should be a multiple association. So that motivated us to go beyond this binary structure. So when we talk about graphs, we only talk about a pair of nodes which is connected through an edge, and this sort of physical reality, when we tried to address, we thought, can we go higher? And it turned out, yes, we can. There should be multiple objects which should be clubbed together, which means in the language of a graph, more than a pair of nodes should be clubbed together to form one data structure. And when we did that, some sort of this thing, that is called hypergraph. So it's not a binary edge anymore, it's a data structure where you club more than two nodes together, and it's called a hypergraph. Okay. And you can go to any arbitrary, and once you set up this notation, you can actually end up like just establishing all possible endpoint correlation functions sort of thing. Earlier you can think only the binary structure, you were looking into 2-point correlation functions. There are things to extend. So just let's not go into details of this, but what we ended up doing, that for like the same event reconstruction problem, we set up some hypergraph learning methods and did the problem more accurately per se. So here we sort of published our paper where we showed that like we had a regular particle flow, then we have graph neural networks, and then we went to hypergraph neural networks, which is now like one of my tasks in CMS is now to just bring the ideas of this paper inside CMS, which we developed. So you can see like in what context it works. Like when you think about like order of 100 nodes and like number of edges order of thousands, there you can construct graphs and hypergraphs to solve a very complex statistical learning task, and it sort of works pretty well. So this is absolutely new direction of development which we are doing. Okay. Then comes to another problem which I sort of, these are my personal favorites, so I am talking about them. This is a bit physics motivated way to construct a neural network. So one of my favorite thing is heavy flavor decay. Heavy flavor, when B hadrons, D hadrons, etc. decays, the signature is that they always have a secondary vertex inside the jet, which is not there if a light pattern converts into a jet or a gluon fragments into a jet. So whenever we talk about B tagging, C tagging, the core experimental problem becomes you have to identify whether or not there is a secondary vertex inside the jet. Okay. So here you can see this idea that B to D transition happens through weak interactions. Okay. And this average displacement like length is beta gamma times tau, where the average tau in the rest frame of the B hadron is 1.5 picosecond. So how do we figure out there exists something here? So roughly what we see that the hadronization time scale is lambda QCT inverse, and what we measure are this calorimeter energy deposits. So we have to set up something to do that, and we did that. So what we did, we just figured out a graph neural network and built something to figure out whether or not there exists a secondary vertex inside a jet. Okay, and that was sort of cool stuff for me. And when we really solved the problem and implemented inside Atlas, that became the default Atlas B tagger, which, and if you see now the Atlas web pages, some improved version of the idea which we had developed and is now introduced, and it surely sort of turned out to be well performing. So it was one of the cases where you really have a physics problem in hand, and we went out and solved that, just find the secondary vertices inside a jet. So the whole idea is that you have a bunch of tracks associated to a jet, and you just do a partitioning of that set, that which tracks are originating from the primary vertex versus which tracks are originating from the secondary vertex, and try to figure them out. So that's nice. And what became the direct physics consequence of that? This is my favorite physics problem is try to find out charm Yukawa. Like if you see Yukawa interaction, we know that Higgs talks to top quark, we know Higgs talks to bottom quark, but in the quark sector, finding out the Yukawa interaction with charm is sort of the holy grail for next few years. And you can see that, I mean, this is not the updated plot. The updated plot is something more. So earlier, let's say in 2015 or 16, the upper limit on the signal strength. So if you don't know what is signal strength, like when you don't have an observation, you put an upper limit. And when you make better and better measurements and things like that, you bring down the upper limit. So in 2015-16, this upper limit was like 100-ish. And now, with advent of all this machine learning technique, we have brought it down below 10 actually. Like if you see the grand combination here, this is not the updated plot. So right now this number, the combination is below 10. So it's sort of now guaranteed that in coming decade we will see charm Yukawa interaction. And when LHC started, no one could have even dreamt of this statement. And now, I mean, this is what machine learning brings to physics, that what nobody could dream about is now, like, if we can't discover it, it will be our failure. We should see it. Now, there are some other examples I want to show you. That there are all these boost invariant networks. So, Lorentz group equivariant networks, where the accuracy of a boosted top identification is sort of, you see that if you really exploit the Lorentz group symmetry, keeps sort of constant, whereas if you apply a fully connected network for highly boosted scenario, the top tagging identification decays, which means this is a demonstration that you can actually make your neural networks to like understand the global symmetries of the problem, and they actually help you learning the data, and those are tested out. Okay, although we still don't know whether it will work in data or not, because when a particle deposits energy in the detector, all this Lorentz symmetry, etc., are lost. So we need to check. Okay. Then I come to discuss a little bit on the other direction, which is like generative model. Right now I was talking only about like supervised model and things like that. So in the generative model, what happens that you are given an data X. You don't know from which like what underlying probability distribution that data set is following. So if you want to just produce more and more data sets which are following the same probability distribution which is unknown to you, the first task should be just let's try to figure out what that probability distribution should be. So we try to do it via help of a neural network. We have a finite sampling of a data. We don't know analytically what probability distribution that data is following. Through some statistical learning task, we want to figure out that probability distribution. That's generative model. So one is the thing is called adversarial network. So this is the diagram of something called a GAN. GAN is like generative adversarial model. So what is the idea? The idea is that I have some real data, okay, and I have some like random number space which I called latent space. So I simultaneously train two networks. One is called a generator, another is called a discriminator. What's the task of the discriminator? The discriminator is fed two pieces of data. One is real data, another is fake data as produced by the generators. And the task of the discriminator is to discriminate which piece is a real data and which piece is a fake data. And then once initially the discriminator can find out which one is a real data and which one is a fake data, it passes that information to the generator, and the generator tries to improve its performance by producing fake data more accurately so that this newly updated fake data look more and more realistic. Okay, that's the task. And when this tug of war, like going on, a tussle between a generator and discriminator, finally when an equilibrium stage reaches, then it happens such that the generator starts producing fake data which are indistinguishable from real data as seen through the eye of this discriminator. So it's almost look identical. So if you do like all this video editing kind of thing which you see in the internet, where you know some random words on a video on face of Obama or something like that, this is the case. Or if you have a laptop, you can type something like this person doesn't exist.com. You will be led to a website, and every time you refresh the website, you will see a new human figure and none of those human figures are real, they don't exist in reality, but just by looking at those pictures, we cannot say that whether those person, there is nothing artificial of those person, like I can just fake you that this is my friend and you can't just deny me. So that's the case of this, like now the real fake generations are at so much level, so you can always use it for wrong reason to bluff people, but you can use it for good reason. What is the good reason? Let's say you don't have real samples in ample. Yes, Dipanshu.
So in this whole process, generator is learning to create more and more realistic data. But is there something also going on with the discriminator, or is it fixed?
No, it's not fixed. It's trained. It's trained. So, but first it's initially pre-trained so that it really can discriminate initial stuff like what is completely fake versus what is realistic, and then it's also simultaneously trained. Yeah. Okay. Good. So there is so there are something like loss function like this. There is something called min-max loss, and there are many interesting underlying statistical learning theory which is going on, because whenever there is a tug of war between the generator and discriminator, there can be an equilibrium region where none of them are winning, and in that case the training itself can stall, and that is something very interesting scenario. So after all, then we know right now this generative. Yeah.
So one question. So here, if I understood correctly, one can produce more and more fake samples which look like true ones. So the discriminator also, as he was pointing out, so does it also learn to discriminate between these two?
Yes.
So, like for the purpose we have at hand, why does one need to generate these fake samples? What could it?
Right. So one of the example is that, let's say in our context, in LHC, we need very large computational power, right? But if you ask for what purpose we need so much computational power, the lion's share goes to produce simulations. Because in LHC the detectors are so complex that simulating one event in a very good like able computer takes 1 hour, and it's millions of events which we need. So so instead of a real simulation, now if you can train a neural network which can just produce pseudo events just by producing, let's say, so-called fake events which looks as realistic as the real events, in the sense that both of them will follow the same probability distribution. Then you can bypass all this very expensive CPU hours by putting something in a neural network, and it does a simulation for you, and it reproduces the simulated events which are done very fast.
But one of the main goals of generating such large number of events is to sort of reduce fluctuations, say in the tail, or populate more events along the tail, say of a QCD background.
No, not necessarily. Like the whole simulation is not just the QCD background. It's just bypassing. Let's say we want to bypass the giant step, because the detector simulation is what is really expensive. It's not the matrix element which is most expensive. Okay, in terms of CPU hours.
Okay, but it cannot generate new parts of the data, like it will try to replicate what kind of distribution you already
So
have.
that's true for any neural network, that neural network can't produce new stuff which it hasn't seen. It's just generating more stuff.
Okay, so the GR simulation which takes time, that you transfer.
Exactly.
Okay, thank you.
Yeah, Padmanath.
Hello.
Yeah.
Now that you have this expression on the right hand side, in the black box, I was already thinking that you can see these GANs as some chi-square minimization again.
So
right?
So this is like a simpler version of the generative models called autoencoder.
But this is again basically very much like chi-square.
This is chi-square. So this, what this is telling is that you have an encoder network and a decoder network. You have given some x as input. So you first pass it through an encoder. So g of x is an encoder which is like a compressed information as latent space, and you pass that latent space through a decoder to create some pseudo data. Okay, and how do you know that your pseudo data replicates the original data? You tend to sort of do a chi-square, like Euclidean distance between the pseudo data and real data to see if it's coming close to zero.
So the main difference between a standard chi-square minimization and this program is that your variables appears in both terms inside the chi-square, right? Your
Right.
xi's are appearing in both. So one place it is actually lying as it is, the other place you use it
Right.
to regenerate the similar things and then try to
Exactly.
differentiate.
So let's say the generated stuff is x prime, which should statistically look identical to x. That's the whole purpose of this game. Now, whether that's the case or not, you can make a distribution of x and x prime, and you can make Euclidean distance between these two distributions, and that should go to zero. It may not be the case that individual sampling from x and x prime are looking identical, but the statistical envelopes should look identical. So you make a distance among two functions, the distributions.
Maybe you will be speaking about it, but at what stage do you will you start thinking your generator is efficient enough to generate fake samples that really imitate real samples? Because actually, if you consider these LAE cost functions, these are basically positive definite, and you naively expect that to go to zero to have a best scenario.
Yeah.
But
So in reality, it never goes to zero. But then it's the question like how do you know in general a generative network is trained well enough? So you just again just generate a new sample and make normalized distributions which should behave like PDFs. Okay, and those PDFs should be similar compared to the original data. And when you can ensure that's happening, I mean, you have to construct mathematical quantities to check that depending on the physics problem you're doing. But once you like assure yourself that's the probability distribution functions from the real ones and the fake generated ones are sort of looking identical, then you're sort of okay to use them.
so it's not just the LAE that you show here, but some other observables also you utilize
Yes,
to actually make sure that things
absolutely. I mean, this is just a schematic, broad conceptual slide.
thanks.
Yeah, yeah.
I mean, for LHC, for instance, so far we were talking about these momentum inputs, right? Px, Py, Pz. So they need to be as accurate as possible, right? So how can an average description
No, look.
not mess with the
Wait,
particle identity?
I think this needs to be addressed. After all, we are trying to make inference about a quantum mechanical system. So everything that can be done is to talk about expectation values of the system. Okay, so now in LHC context, when you talk about distribution, it's not that every event by event has to match. It's just when you talk about a distribution, tail of a distribution, it's the statistical pattern of the distribution which you're talking about. So if there is any peak in the tail of a distribution, that's part of these PDFs that has to reflect in the expectation values.
But won't resonance, suppose the Higgs peak, I mean, that we expect some number of events, right? So
Right.
that event number is also, even if the structure of your generated
So
distribution
that-
is similar,
So that number of events is proportional to the luminosity at which you are operating.
yes.
So now when I talk about normalized distribution, it's the differential cross sections, right?
Yes.
So as long as you ensure that is coming correct, then you sample n number of times depending on your luminosity, and if that differential like normalized distribution has that little bump hiding in the distribution, that will pop up when you multiply by some finite amount of luminosity.
Okay. So the number of events or something that is not
Number of
relevant.
events,
Or
each
the cross section, suppose I
the
say
cross section is the important part, where
the cross section.
the cross section is what which determines the probability distribution, right? It's not the events.
Okay.
Every event is an independently identical statistical experiment.
No, I was meaning like sigma times luminosity will give me the number of
Yeah, but so there
events in that.
the luminosity, like if you increase the luminosity, number of Higgs events will increase.
Correct.
So that doesn't capture the physics. The physics is captured through the differential distribution. It's the cross section which captures the physics.
So that is the goal, that if your
That is the goal.
GAN generated data set
So
reproduces that.
yeah, so
that's
that's
something we
why I
believe.
started actually here. So figuring out the underlying probability distribution functions, which for a particle physics problem is for a scattering experiment is determined by the cross section, right?
Right.
That is the most important thing to understand.
Okay. Okay. Thank you.
Yeah, Dosh.
I have one question. So, let's say I have, let's say, generated through this network, generative network, some events, and for that I need to train with like some real data. So real data is basically a collection of some variables. Okay. So now let's say I design a new variable. Okay, and which should ideally, let's say, give me some extra information, let's say for some rare processes or some discrimination variable. And if I do not, let's say, generate the events with that new variable, whether these like method will work, or what do you think?
So like let's say you have some new variable, then I would say for practical purpose, feed that variable at the start of the training.
Yes.
Then
let's say the generation has already been done, and now let's say.
So it needs to be checked case by case, but ideally the generation, if it's done, it should capture the probability distribution function. Now let's say you make one sampling from that probability distribution function, it can replicate an event, a jet, something else. Now a new variable means a new combination of the informations which is associated with this object or the event itself.
Exactly.
So you can cross check whether it works or not. I mean, if the training is perfect, ideally it should work, but nothing is perfect. So there can be some little mismatch, etc. Then you need to go back and see your training, how you can improve your training.
No, so the question that I am asking, let's say I'm interested in quark-gluon separation. Okay.
Okay.
Okay. And let's say I have generated some data from the QCD in order to replicate the QCD background, where I did not put in any substructure variable to generate those data. Okay. So for example, now I want to, let's say, look at the energy correlation function from the let's say data, and try to use that to discriminate between quark and gluon.
So in that case, the answer is it won't work ab initio, because energy correlation functions are new pieces of information. So when you add that pieces of information in the initial data, it's a data living in one more higher dimensional representation, and the probability distribution function in that higher dimensional space might look different. So initially the neural network didn't know what that higher dimensional probability distribution function is. So it won't serve your purpose. So the thumb rule is like just start with the maximal amount of information you have in hand and feed the neural network that information. Like unless you teach neural network something actual information which is there with the data, the neural network won't learn it out of the box. Good. I mean, neural networks are not magicians. It just learns what you teach them. So that's the thing. Great. So, and there are, okay, so another class of generative model which are flow-based model. I just don't want to get into the maths in details, but these are like converting functions to smooth functions. So earlier we were talking about generating new data. So now we are talking about if you start with a distribution, how can you generate directly the probability distribution function itself? It's a conceptually different concept. So earlier we were trying to generate new set of data and indirectly trying to learn the underlying probability distribution function, which were these adversarial networks. But now here there are flow based methods where we are directly trying to understand the distribution functions itself. And I mean, many QCD applications using lattice, including lattice QCD applications, use these flow based models. Like they try to directly like regress these Wilson lines and stuff like that, so on and so forth. And what I'm not going into something called diffusion models, and there are now like last 2-3 years there have been like a tsunami of such things called flow matching and conditional flow matching. So unless you're an expert, this might turn out to be jargons for you. So I will just try to show it. Like you tend to regenerate a data by first noising and later denoising, and they somehow works better than the adversarial networks which I was talking about. Now there are mathematical understandings why it happens in such a fashion, but I just wanted to highlight that if you want to learn them, you may directly start with diffusion models, so on and so forth. So just giving you a perspective that in the case of generative models where we stand, we had a GAN where discriminator and generator, we had a autoencoder where we had encoder and decoder network, and then in the flow based model we directly had access to the distribution functions f themselves, where we can also compute the inverse function. So I give it an x, try to encode the data in the latent space z to some flow based model, and then try to invert that data through inverse flow based model, so on and so forth. And in the diffusion model, I iteratively try to noise the data, go to the latent space, and then try to denoise the data and come back to some another replicated instance of x. Okay, these are the things which are going on in the market. And yeah.
An expert, definitely not an expert, but these diffusion models, you said you gradually add Gaussian noise and then reverse. Now when you add Gaussian noise, you mean that you are actually adding up the pixels and just replacing it with single
Something
pixels.
else.
So basically you are losing resolution.
Yes.
Now if you want to take reverse process, then you basically have to split single pixels into smaller and smaller ones.
No, it's like given a pixel, I distorted it, and then
Given a pixel, given multiple pixels, you merge them.
So like let's say I have like 20 by 20 pixel. So each pixel originally had some value. Sorry, yeah. And then I start adding noise to each of the pixel. Like each iteration of noise adding is a stochastic process, right? And then when I invert it, denoising it, that each iteration is also stochastic. Okay, so from where I started, I will never come back to the same place.
What I'm puzzled is actually in the reverse direction, you will basically be losing more and more information, right?
Like once I have like added noise and gone to Z, I have scrambled up all the information, right? So now we need to understand what do I mean by losing information when I have completely scrambled up my information. It's there somehow, but it's hidden, not accessible to me. Okay, so now when I will denoise, maybe I will removing some noise, but I may also remove some original stuff, right? And that's if I just remove the noise and not original stuff, then I would have landed back to the same picture. The fact that while denoising I am also adding stochasticity, that's making me land up to in the reverse path, landing up to a new point in the data manifold.
Maybe I am understanding it wrong, but if you actually add a Gaussian noise and you go on doing basically these again some flow diffusion, etc. you go on doing Gaussian noise, at some point you will basically see that all the pixels are basically noise. And if you now just simply remove noise, what is left is just a constant across the entire
But removal of noise is just not like a constant subtraction. Okay, that's also like you can think of
I see.
removing noise is also like removing some Gaussian terms from each pixel or something like that. It's not like you started with a colored image, you added enough noise, it became completely gray or white, and then you're doing a constant removal. That's not the case. In every iteration, then at each pixel, you're removing is also adding negative stuff, right? So you just do a reverse process so that you ensure you end up somewhere in the data manifold, but it's just the other way around. Yeah. Great. Now, I just want to show you this generative model performance and things like that. So this has now become very standard in our community. It's becoming that we have some simulations. There are complicated Gian stuff. We want to bypass that, and we replace it by something called like generative models, and they can be made like equivariant and stuff like that, so on and so forth. So I want to show you the real advantage. So here for the like a Higgs simulation, Higgs to gamma gamma, you see I have a real Gian4 simulation, which are the black dots, and the blue and the red dots are something coming out of neural network simulations. So if I take a pair of photon which is coming from Higgs decay, I should be able to reconstruct the mass. And the fact that it learned correctly is that from the generated, let's say, pseudo samples, when I reconstruct the Higgs mass versus I compare with the original sample, I'm not losing the mass and width of the reconstructed Higgs. So this is one of the demonstration that it works. Okay, that I know of physics, how it should look like, I know it for the full simulation, and now I have generated something with the generative models, and I have done it. Now, how are we gaining in terms of the CPU time? So here you see that when we try to simulate particles of higher and higher energy, when a higher energetic particle enters in our detector, it creates more and more shower steps. So simulating them are sort of exponentially rising with the time. So that's the demonstration. It's a log-log plot. So the number of average CPU times goes as exponential with the in a Gian4 simulation with the increasing particle energy. But when we try to do it through a neural network based generative model, this sort of flattens out. So in terms of CPU computation time, this is a huge gain, and without actually missing out any physics. And here we have checked for like electron showers, hadron showers, etc., so on and so forth. So this is where our actual advantage is, that we are creating pseudo simulations and trying to bypass Giant, and we are not losing any physics information. We can really use them for our reliable physics studies. Okay, and this is a huge gain. I mean, you can think of like a number which is like 2 into 10 to the power 4 versus 50-ish or 60-ish. It's a huge amount of advantage in terms of practical reality. And we are also doing it for particle flow. So the idea is that the whole particle flow was like, if you have a bunch of hits, you construct reconstructed particles. And we wanted to do it for truth particles. I just do a fast simulation using generative model and do the particle flow simulation. So here we wrote a paper to do that. Okay, so there are some complicated objects. Of course, you always have to like fine tune your model, trainings, blah blah blah. But eventually, you can prove a proof of principle that this kind of things work, and so on and so forth. I can let's see. Yeah, I think I can walk down through the rest of the slides. Like some other things which are quite interesting happening these days. For any search, new physics search, background estimation is the most important point. And here, when we are looking for, say, di-Higgs to 4b kind of background, those are sort of rare. But when we are looking for double B distribution, 2B jets, there we have sufficiently enriched background. So, one of the thing using flow models we are trying to do is that from 2B enriched background region, we are directly trying to predict the spectrum of the 4B background region. And so this is like a mapping from a distribution to a distribution, which was flow model, and this is like directly trying to access where the background is too low, where we cannot rely on event by event Monte Carlo. Can we directly predict the distribution function, starting from a distribution function where the background is enriched enough. Okay, so these are part of mainstream publications right now. And now another thing which we are trying to bring in explainability. It's still not very much on the rock solid details, that when a neural network infers something, what information of the input data it gives. It's not like writing down few pieces of mathematical steps so that you have real track of which pieces of information are used or not. So finding out interpretability is very important. Those are been attempted for some cases, but it's still on a, let's say, dodgy footing. It's not as rock solid as the previous ones which we were talking about. Another part is uncertainty. You feed in a data to a neural network, the neural network gives you some output. How do you know what will be the amount of uncertainty on the output data? So there are community-wise, like there are different kind of stuff. People try to do small like variation of the parameters, and depending on the strategy you're taking, you may have different amount of uncertainty. So there are yet room to zero down upon the case that what will be the true uncertainty, like prescription for uncertainty estimation, and then we can have an uncertainty band on top of the output of the neural networks. And until we can do that, we can never quote whatever number we are predicting is accurate. So those uncertainties are equally important for us. Okay. So there are many methods which have been tried, Bayesian networks, then ensemble methods, so on and so forth. Our communities are trying all this. If you are interested, you can try your hand in one of these, and these are actually going to be very impactful contribution in the domain of high energy physics, that when we are using neural networks so much and we are predicting some observable, measurable, how do we estimate uncertainty on our observables? Fine. Maybe I will talk a little bit about the anomaly detection, which is also going on, although I personally don't believe in this. I just gave it because people are trying it. So there are things called outliers in the probability distribution. You have some instance of the data which are not following the pattern of mainstream probability distribution. How do you figure out the hiding wolves in the data? That's the story of anomaly detection. There are different test statistics which are being conducted, like over density detection. There are some regions in the parameter space where there are bumps in the data. So these are the cases of bump hunters which people try to do when people try to seek for resonance search. And then there are some outlier distribution, like completely in a different region of phase space, there are some additional distributions. Okay. So there are weakly supervised learning methods which have been applied, like you don't know which object is signal or background, etc. So people have done like a parameter search. I'm not very much fan of this and things like that. And there are automating ABCD methods which are used for all these tasks. Like ABCD method is a background estimation method, which is something you needn't know unless you are truly an experimentalist. But in terms of background estimation methods, these several methods are used. Okay. So just to show you, this anomaly detection using machine learning is a hot field which is going on quite a lot. So you can see that there are over densities which have been predicted, and there are like open data sets, simulations in which people try to apply their improved version of anomaly detectors to figure out if they can do the bump hunt properly. So, I mean, if you are interested, you can try. Great. There are open data sets for all these ideas which I was talking about. So if you are interested in machine learning and high energy physics, there are community standard data samples, codes. You can just bring your improvement on top of that, and that will be fun. Now, the next frontiers is going something like the topological neural networks. We already have graphs. We already tried hypergraphs and the generalized version of combinatorial complexes with higher order structures on this graph data set. And for me, this is really interesting. Like really, how do you take out the last piece of information which is hiding in your data representation and can deploy them, finding the and can solve the real hard tasks. So this use the topological data structures of these combinatorial complexes and write neural networks to solve this problem. This will be really interesting stuff. Okay. So I just want to then just wrap up that, you know, if you talk about machine learning and high energy physics, it's going to stay with us for significant amount of time. Some random ideas may come and go, but next 10 to 20 years, like development of machine learning ideas which can solve real complex high energy physics tasks, that will be there with us. And irrespective of like what you're trying to do, like you can make some general aspects out of it, be it interpretability, solving some generative model and things like that. And what we try to do, we always from the Collider community try to reach other communities and try to make crosstalks. And some glimpses I wanted to give you, that not only we the experimentalists, but also cosmologists are using it, theoreticians are using it, lattice field theorists are using it. So it's becoming like everywhere. It's just our task is to figure out, are we asking the right set of questions and are we doing the right set of jobs? So there are plethora of things to do, and if you are interested, try your own hands. And yeah, also I just want to advertise that every year we conduct a machine learning school where we actually do real hands-on stuff to teach you the kind of concepts which we are talking about, how to actually write the codes to reproduce some of the stuffs which I showed. So next year again it will be in July. So if you are interested, just sign up and we will see how we can just try to teach you to do this. Actually, you can do it yourself. So yeah, thank you. Any further questions? Okay, there are more questions.
Is there any question? Oh, you have questions.
You just took out the mic from Padmanath.
Actually, I have two questions.
Yeah.
One on outliers.
Uh-huh.
So
Let's go back to the
it's
slide.
not anything particular with the outlier in the phase space or even a dense set of points. But okay, one can identify the outliers. But once you identify the outliers, what do? Do you just throw them away?
No.
Or do you just increase the statistics to make sure that?
Yeah, you want to figure out if they're outliers, that means they're following a different probability distribution functions. Because otherwise, in a statistical sample, how come there is a density of outliers? That means if there are mainstream
Because
distribution.
in statistical field, you can actually have some phase space points which are far away, which has very less weight, statistical weight, and in your, let's say, Markov chain Monte Carlo, you at some point you just hit that. by
Right.
mistake.
So when in statistical field theory, when you hit that at the end, it means the intermediate regions already you have some handful of statistics. But here the problem is the intermediate phase space has no statistics, and suddenly some remote corner of the phase space starts having some statistics. So that can only happen if those like outliers are following a different probability distribution function, which you have no idea about. That's not following standard model distribution.
What do one do with it? You
So
just
like
throw-
if then you will put answers of new particles, new physics, etc., and try to
I see, I
explain
see.
them.
Okay, so this is the way you identify if there
Yeah,
exists
yeah.
new particles, etc.
Yeah, exactly.
I see, I see. Okay, second question on errors.
Uh.
You had a figure on all these different error estimation procedures. So, thing is, I believe I basically practice this stochastic MCMC, Markov chain Monte Carlo, right? And if I understand correctly, Bayesian methods are basically where you input some priors into the.
Yes, you have a prior, you have a likelihood, and then you have posterior.
I see. Okay. Okay, thanks.
Yeah.
Hi. So one problem we were seeing last time was this pile-up removal. So do people also use ML for pile-up removal?
Yes.
Because the distribution should be known for
Yes,
that
yes,
also.
absolutely. I mean, you throw all the jet, and it's like a node identification problem. That the pile-up particles, since if jet is a graph, pile-up node particles should appear as some node, and then you decide it's a node classification. Which of the probable nodes are from pile-up? So you do a classification, node level classification task to identify them.
Okay, and for triggering also does ML, I mean, are these processes fast enough to be applied at the trigger level
So
as well?
that's why you try to construct this ML on FPGAs, where the inference time is much faster, so that you can use on trigger. But trigger level ML is now widely under application.
Okay, and one more thing. So last time we were seeing these fat jet reconstructions, and like today, the Higgs peak we saw, that seems like a very nice Gaussian feature. You have, yeah, both sides are very symmetric. So in the fat jet case, I think because the jet is wider, there were probably softer things which were not being filtered out properly. So do people also try to improve those filtering procedure? Like you talked about boosted tops and boosted things. So those ML taggers, do they give better symmetric distributions?
So the people just try to use, like, I have a jet which like large radius jet which may be contaminated with pileup, etc. Just feed it into one neural network and give me the right set of particle, and then try to see whether the reconstructed mass is smooth or not with improved resolution.
So it does improve
Yes.
a lot. Okay.
It does.
Okay, thank you.